Hello and welcome to part two of this week's lecture. In this lecture, we will cover what is a fluid and what is the scope of fluid mechanics and its applications, what are the properties of fluids, and finally, we will look at different systems of units and dimensions. By end of this lecture, you should be able to define fluid and its properties and understand different systems of units and dimensions. So we start with by looking at what is a fluid. So we know from our elementary science that there are four states of matter: solid, liquid, gas, and plasma. And if we look at informal definition of fluid, so it's a substance that has no fixed shape but takes the shape of the container. So if we look at this definition, we can see that we can exclude solids from this from fluids because the solids tend to have rigid structures. We can also remove plasma from fluids because as engineers we tend not to deal with charged particles. So we have the remaining two states that are gases and liquids. So fluids are actually gases and liquids, and the most common examples are water and air. Now we know briefly what is fluid. Now the second question is that how it differs from solids. And for the case of solids, the molecules are close together and the intermolecular forces are large enough to give these substances their rigid structure. So the reason the solids have rigid structures because the molecules cannot move from their point of reference. And we have two types of solids. We have elastic solids and plastic solids. So elastic solids are materials that deform under a load, but once you remove the load, they revert back to their original position. And a common example is elastic rubber, for example. For the case of plastic solids, the substance deform under the sufficient load, but once you remove this load, they do not revert back to their original state. And the examples are plastic and, for example, bubble gum. In contrast, for the case of liquid, the intermolecular forces are not large, but they are large enough to hold the elements together in a way that it gives these liquids a definitive volume. So, for example, if you pour this liquid in this beaker, the liquid will not take the whole volume of the liquid, whole volume of the beaker, and it will maintain its own volume. Another way the fluid and solids are different from each other is how they behave under the application for stress. So, for example, for the case of solids, if you have, for example, two plates and in between these two plates you have this solid block and the lower plate is stationary while the upper plate can move. So if you apply tangential stress on this plate, you will see that the solid block deform from its original position. But once you remove this stress or this force, it will revert back to its original position. In contrast, for the case of liquid, again, imagine that you have these two plates, and in between this plate, you have a block of fluid. You can imagine this as, for example, you have a plate of wood on a pond. So, if you apply some force, tangential force on this block of wood or this upper plate, the liquid element or the fluid element will deform and it will continue to deform under the application of stress, and even it will deform once you remove the stress. We can, based on this, we can define a fluid that is a substance that deforms continuously under shear stress, in contrast to solid that do not deform continuously under shear stress. Okay. So we have two types of fluids. We have gases and liquids. And for the case of gases, if we again look at their molecules, we can see that the molecules are further apart from each other and they have very weak intermolecular forces. and the gas molecules tend to expand indefinitely. It means that the gas molecules always fill the volume of the container. So if you, for example, put them in a small container, they will take the volume of the container. But if you put them in a larger container, the same amount of gas molecules will occupy the volume of the larger container, as you can see here, for example. While in contrast to that, for the case of liquids, as I said before, the liquid does not fill the whole volume or the extra volume of the container and maintain its own volume. Okay. For the case of gases, we also have what we call vapors. So vapors are actually gas molecules that are at temperature and pressure conditions that are very close to liquid phase. So it means that if we reduce temperature or we increase pressure, the gas molecule will condense. So for example, steam is a vapor, but if we reduce temperature or increase pressure, it will condense in the form of the water. While in general, the gas, what we call gas molecules, are actually molecules that are further away from the temperature and pressures that are close to their liquid phase. So we mainly distinguish between vapor gases in a subject what we call thermodynamics, and this is something where we study the effect of temperatures and pressures and the phase changes. So now we know what is a fluid, and you might come to this realization that we are surrounded by fluids everywhere. And here I put just a couple of examples of fluids around us. The life around us is significantly depends on fluids and how we interact with them. For example, we have animal habitats, we have different weather conditions, and how we actually manipulate these fluids to our advantage. For example, mixing different fluids, flying aeroplanes, and pumping of liquid and several other applications. Our body itself is a marvel of fluid mechanics, and the air we breathe and how the blood runs through our body is mind-boggling. So you might have heard of mechanics in your physics, for example, where you discuss solid mechanics, that is essentially Newton's laws. So just to remind you what is mechanics. So actually it's not this. So mechanics is the study of effect of forces on a body. So in fluid mechanics, we look at how these forces affect these fluids, or how these fluids behave under the application of these stress, these forces, for example. And if the fluid is at rest, we call it fluid statics. And if they are in motion, we call them fluid dynamics. So fluid mechanics actually use the same principle as solid mechanics. It has the same definition of forces or same concepts of forces, but it is much more complicated in the sense that for the case of fluids, it is much more difficult to distinguish between individual elements. And for this unit, we will actually use realistic pressures and temperatures. Okay. In fluid mechanics, we have different branches. For example, as I said, statics deals with fluids at rest. So when the fluid is at rest, what kind of forces are involved in that fluid. Then we look at fluid kinematics and fluid dynamics that deals with the application of these forces and with the motion of the fluid. We have classical hydrodynamics that actually is development of different mathematical models where we consider our fluids as ideal material. And then we have classical hydraulics where we look at experimental approaches, where we talk about experimental observations of realistic fluids. And what is the difference between ideal fluid and real fluid? We will cover that in detail in the next lectures. Then we have more advanced modern fluid mechanics that actually combine the mathematical principles with experimental observations to drive solutions for more complicated situations. And finally, all this serve as a gateway to the concept of computational fluid dynamics. So, for example, where we develop numerical solutions for very complicated practical situations. For example, models numerically for turbulence that are actually not easy to solve analytically. Now, to give you some idea of why it is important to learn fluid mechanics, we will discuss a few applications in fluid mechanics. Maybe it will inspire you and pique your interest in this topic, which I think is fundamentally pretty interesting. So one of the most common examples for chemical engineer is the industrial pumping system or the piping system that we use in industries. For example, you might be selecting a pump in order to get desired amount of flow rate, or you might be sizing the piping so that you don't have too much pressure drop along the pipe. So we will get into some of these issues in detail in this course in the next coming lectures. Another application is actually that is also where fluid mechanics is central to the design of electrical systems. And here we are talking about, for example, coal power plants and gas power plants and nuclear reactors. So this fluid mechanics is how we deal with, for example, the flows in boilers and condensers, and the flows of cooling, for example, water in nuclear reactors themselves. So this is all covered under fluid mechanics. And finally, because of the more recent concerns over climate change, there is a growing interest in renewable energy, for example, and it's certainly a growing field. So fluid mechanics is central to the design of many of these renewable energy systems. For example, hydroelectric plants and other systems like geothermal systems, and designing safety measures in case of flooding. So all this covers under the scope of fluid mechanics. So that's the end of this part, and in the next part we will look at different properties of fluids. Thank you so much for your time.